expression of I square with this, because IS as you can see, IS, what is your IS? IS is VS by RS, R dash by S plus J XS plus XR dash, isn't it? That's your IS. So if I take this one as X, which I have assumed X is XS plus XR dash. If you square, so it is this VS square, and the denominator, the imaginary term, they will come as A square plus B square.
So the power factor is implicit within that statement.
We are not talking about the power factor. Power factor, we are just talking about magnitude. Okay? Everybody happy with this one?
Yes.
Anyone? Which one?
J.
Yeah, so no, that means, see, if I have something like A plus JB, so magnitude will be what? Magnitude will be root over A square plus B square. So if you take the square, your square root goes. Okay? So A square plus B square. So that's what we are having here. Everybody clear? So now this one, if you just solve this one, what do you get? So I write in one line, so I will have like this, S V square, here I will have S RS plus R dash whole square plus A square X square times R dash. Agree with me? So I am adding SRS plus R dash whole square. This S square will also be here, S square X square. Clear? And S square will go up. One of the S square will cancel with S. So that's why there will be S here and R dash.
So how did that become S square?
Which one?
There's an R dash on S, so there's S squared everywhere, but you cancel one of them.
Yeah, so this
Yeah.
is,
No, the one at the bottom.
In front of X squared.
In front of X square.
On
In
the
front-
S squared, it's the same as taking it outside the S brackets. So you've got an S inside
yeah,
brackets, so
okay,
take it
okay.
out and use the square.
okay? So now, so this is my top. So this part I don't need. So that's my P air gap. Now you need to use this one. So T develop. So on there, I want to go for T develop, which is my expression here. So P air gap, which I have got 60 by 2 pi ns. So 60 by 2 pi ns times 3 s v square by, so let us say this is in Now actually we can always make this type of equations and we can vary s from 1 to 0 to plot the torque at different s. But as you know, the induction motor was developed in 1887, 1888. Okay, long time back, and that time computer was not there. You understand? Computer was not there. Even calculator was not there. So people find out the torque speed characteristics approximate way. So I will tell you how do we get that. Of course, today's circumstances we really don't need that way of doing. But that time the people were very, very smart too. Okay? So let us say when A is equal to close to 1, starting. So S is very large. Okay? S is very large. S is 1 means S is large, isn't it? Value of S varies between 1 to 0. So S is 1, that means S is very large. So if you approximate the term, what do we actually get? Approximate. 60 by 2 pi ns all will stay, isn't it? V square, 3V square, all will stay. R dash will stay. So you have S at the numerator. S is the numerator, and because this part is the resistance, your reactance is usually very large, so you can get only this. So S square, X square. Because this is very large compared to this. In any circuit, your reactance is usually very large compared to the resistance. So you can ignore the resistance part, you keep only reactance. So now S and S square, so what you actually get, the T developed is inversely proportional to
1 over.
Do you get? I mean, this is of course, as I said, this is of course you don't need today because we have computers, we have smart calculators, we can do that, varying from S equal to 1 to 0. But I just want to tell that how at that time people got the induction motor characteristic. So when S equal to 1, that means at the time of starting, you get your torque is inversely proportional to the S. When S equal to 0, that means running at full load. S is very, very small. So what you have, T develop, that part of course it will be there, 63 ds square r dash 2 pi ns.
So we don't consider the reactance this time, right?
We don't consider the reactant this time,
Okay.
only we consider r dash square.
Yeah.
Okay? So effectively what we get here, T developed is proportional to S. So you got one region where T is proportional to S, another region you get T is inversely proportional to S. So now if I draw, so this is my S, okay, and this is my T or T develop, whatever it is. So let us say this is close to S equal to 0, this one, okay, and this one close to S equal to 1. So I don't know where these characteristics will meet, but I can say that when S equal to 0, my torque is in square proportional to S. It's just linear. You understand? When my slip is close to 0, it is linear, so we can draw a straight line going from the origin. And when S equal to 1, I do not know where it is, but what I know is inversely proportional to slip. So I can draw inverse characteristics like this. So this is my proportional to S, and this is my inversely proportional to S. But we are not talking of two different things. We are talking of one particular thing. We are just dividing the area. So basically, you will say that actually it will be like this. You understand? So it will be like this. So this is the starting, isn't it? And this is your running. So in real life, it does not run jumping from starting. It starts from 0 and goes to running state. So in real life, what will happen? You have the characteristics other way around. Okay? You have the characteristics other way around. So if you draw that characteristics by flipping, so flipping other side, so A is equal to 1 here and A is equal to 0 here, so your characteristics will be like this. Okay?
And that's like a scaled version of torque for a meter.
Yeah, it's called scale version of. So this torque, what is this torque? What is this torque?
Starting torque.
Starting torque. And this is the speed, is synchronous speed. And this torque, so that's the maximum torque you can get. Now starting torque is very, very important for any engine or any motor. See, when you stop, think of that you are driving an electric vehicle. You stop at the traffic and signal become green. You want to go with the motor. You apply. That's the torque you need to have to overcome the static friction. So sometimes you have seen that your engine, your car doesn't have enough torque, but side by there is a very good car, expensive car, shoo, they go quickly because of this starting torque. So starting torque is one of the most important characteristics for any motor. Okay? So when you have the electric motor, you will have this. In the normal car, we don't have electric vehicle for everyone. We use the petrol or diesel. They have a different way of the starting, but starting torque is very useful. Usually starting torque is less than the actual pull-out torque, which is the maximum torque a motor can give. So, for example, you don't think that we will be operating always at the pull-out. We will be operating sometimes like this. So this will be full load. Okay, somewhere like that. So this may be your full load torque. So that's the torque you are expecting your motor will deliver. But then you may say, why do I need to have such a big amount of pull-out torque? You need to accelerate. Also, you need sometimes overload capacity. You do not want your motor to fail when your torque slightly becomes higher than the full load torque. So how much ratio, that depends on like 150 to 180% of the full load torque.
So S is decreasing from left to right here,
S is decreasing because at starting S equal to 1.
right? Yeah, okay.
Okay, so that's the starting. So that's your starting. So that's all about this equivalent circuit. So could you please tell me that where you have got a little bit of problem to follow me? I know that I was going through, but if you follow the actual equivalent circuit and then the analysis, I hope that you will not have much problem.
One of the formulas was torque is P developed on 1 minus S WS. Is that right? So if S is 1, how does that make any torque at all? So 1 minus S for S equals 1 is just 0. So that's...
For P air gap, torque developed multiplied by.
Yeah.
No, that's 1 minus S is cancel, isn't it? We don't have 1 minus S in the final expression. You have?
Oh no, I have it written down on the previous page. So
Yeah, but 1 minus s you will see it will cancel. You don't have 1 minus s in the denominator where you get the expression as infinite. I don't think you get that expression because 1 minus s, both sides they cancel.
Ah, cool, yeah.
So typically the S value running full load is smaller than the S at full load. Is that
So-
usually arranged like that?
So one of the important thing here to see is this part between s equal to 0 to this will be around 10%. Okay, this will be around 10%. So ideally, the induction motor runs very close to synchronous speed. So the slip will not be more than 10%. Full load slip will be 5%, 4% to 5%.
So that's S is 0.1 or
0.
omega is
0.1, yeah. So
Yeah.
this maybe you can say this will be 0.1.
Yeah.
Now these characteristics also called the stable operating region. Stable operating region. That means if you operate in this region, motor will run stable conditions. Okay? So what is the stable conditions? Stable conditions when most of you have done 3 to 4, or those who are doing 3 to 4, they will know. Stable conditions is usually explained with the help of diagram that So I have got 3 situations here. Okay? One ball I keep it here, one ball I keep it here, one ball I keep it here. And then I have some training from another leg. I always kick the ball in my right leg. Okay? So if I kick this ball here, don't need to be Maradona, even anybody else can do, a little kid, then what will happen? This fellow will fall down. Don't know. If you kick here, what will happen? It will go like this, finally. So this one called unstable, this one called stable, and this one called quasi-stable. Why? Because this fellow will come and finally it will oscillate and settle here. So what does it mean? When somebody kick, that kick not means that it's a huge kick. That kick means it's a small kick which creates some disturbance in the system. Okay? So if you create a disturbance in the system and system still come back to the original operating point, that is called the stable operating conditions. So here, if we have a situation that we disturb the system will still come back to the original operating point. So for example, if I have a load torque, okay, if I have a load torque something like this, TL, this is my TL, load torque. I will come back still this point even though a disturbance is created. So these are very important to understand, and this part is the stable operating region. So usually the motor will operate there.
So with the difference in S between the pull-out torque and the 0.1 S, would that be sort of a safety factor?
Yeah, so that's basically a safety factor. Like it comes like whether you prefer a Russian design or you prefer a Japanese design. Okay? So how much you actually keep the safety factor, it all comes down there. You all understand the Japanese design and the Russian design. Unfortunately, Russia don't make car, otherwise you could. But if you think of that, anything Japanese made is very compact, but it does not give you the factor of safety too much. But if you have a Russian system, it never fails because it's like 3-4 times factor of safety. You understand? So if you have a motor, like I can tell you that the university where I passed out in India, we had motors from 1920. Okay? And when I studied 1983-87, still they are very good.
Yeah.
And now, when I go to Calcutta, I visit my university, they still use after 100 years. But if you have a Japanese motor, after 5-6 years, you have to ask money from the university to replace them because it will not run that long. So that difference for how many times it can actually relate. If you want very high pull-out torque, your size of the motor will be big. You cannot make the motor very small. Okay? So that's the consideration.
So
So
talk
we'll talk about a little bit more, little bit later, but I think at this stage, equation wise, I covered most of the things. So one thing here which tells you that induction motor operates at constant speed. Okay, constant speed. Why? Because if the speed changes, you can hardly change the speed by 10%. You can hardly change the speed by 10%. So which you may assume that is pretty constant. Because we do not operate in this region. Okay, so it operates along this region, so it usually operates at constant speed. That tells the problem for induction motor too. That when we have an induction motor, because it operates at constant speed, and in most of the applications, you need the speed to change. Induction motor is not suitable for that type of applications. You understand? You don't think that your application is constant speed. Your application needs variable speed. And that's the reason induction motor is not suitable for those applications. It does not mean induction motor cannot be used. It means that induction motor needs something else to make it run at different speed. Okay? And that's why the speed control of induction motor is a huge topic of interest. So induction motor operates pretty constant speed. So now suppose you may say, can I actually change the voltage to change the speed of the induction motor? Yes, you can do. But what will happen? Suppose this is my voltage V1. If I reduce the voltage, as you have seen, the torque is proportional to the square of the voltage. Okay? If you reduce the voltage, you will have the torque like this. If you reduce the voltage, you will have the torque like this. You understand? So this nature remains the same. Magnitude changes. So what does it mean? This part, it does not change much. So because of that, voltage control is not a technique applicable to change the speed of the induction motor. Voltage control technique was not the method you have. So the question comes now that what can you do to change the speed of the motor? Suppose you want to run the motor anywhere here.
You need to change the synchronous frequency.
You have to change the synchronous speed because this speed is corresponding to omega s. This speed is corresponding to 0. Isn't it? So this speed corresponding to omega s, or also you can say corresponding to frequency fs. So if you change the frequency, okay, you can make the speed of the motor anything, whatever you want.
Does that change the, so let's say you took the frequency of half Fs in that diagram, would that curve shift, or
Yeah.
would it just be a different point on the curve?
So you will have, suppose you have half, so you will get the characteristics like that.
Okay, yeah, so the curve actually shrinks down, it doesn't, you just
Yeah.
get a different point.
So depending on your speed, you can get different frequency, you can get different characteristics. So that was the method we use, and we need inverter. We need inverter to make that happen. Okay. So I think hopefully.
But by changing the frequency,
Yeah, that's what it's for.
changes the voltage as well.
Yes, so that's the one of the topic which is very, very important. So what you need is the fundamental. So for example, that you have the equations, the voltage. Last week we saw like this, F N phi m. Okay, that's the voltage equations for any system. when you apply voltage to a coil, you have this expression. So frequency is the F is the frequency, N is the number of turns, and phi is the maximum amount of flux. Now, if you change the frequency, keeping the voltage constant, what you are going to do? So your F is changing, okay, either increasing or decreasing. In this expression, if V is constant, in this expression what will happen?
The speed goes up.
The flux changes.
Phi will increase. So what is the meaning of phi?
It's magnetic flux density.
So magnetic flux density, so is the core area times maximum Bm. Core area remains constant, so the Bm changes. Okay? So what is the meaning of Bm increasing?
It's
Stronger magnetic
it's the induced magnetic field is changing when you change frequency, right? So the rotation of the field is changing, so you're changing the frequency of the current going through. So the induced magnetic field has to change as well.
No, it comes from, so when your Bm increases, what exactly happened? What exactly happened? Yeah, so it actually, so, okay, so think of that, we have to set up the flux in the system. We have to set up the flux in the system. How do we set up the flux?
You have to change the magnetic field.
How do we set up the flux? What you need to create flux? You need current. So you can create flux by two ways. One by using permanent magnet, one by using electromagnet. So if I say that permanent magnet is not the option, so you need to create flux by electromagnet. So electromagnet means what? Electromagnet means you change current. So this current is setting up the flux. So now you set up the flux like this. You set up the flux like this, okay? So what is this one? This is your H, which is related to I. This is your B, which is related to flux.
Can you draw the graph so I can't see the line?
Or is this color you are not visible? There is no light. Do you have any light? No, I don't see any light. Huh? So I can make it red will be better. So red looks good.
Yep.
Okay. So now this can be actually going like that. Okay, it's going like this. Going like this with a very, very little upward slope. So usually what happened, you are operating somewhere here. For example, you are operating somewhere here. So this much, your B need to be for normal operation, and this is the corresponding current, corresponding H, and H need to be represented by current. Now if you reduce the frequency, you are forcing the Bm to go high. The Bm go high means you will go like this. Now think of that suppose you are increasing by 10%. 10% increase. And that slope is very, very low. So 10% increase means you might have to come somewhere here. You understand? You might have to come somewhere here. 10% increase. And your current is here. That current you might have to go 6 to 7 times. You understand? 6 to 7 times. What will happen? Your fuse will blow. If you do not have fuse to prevent damage, your winding will blow away. Okay? You will start observing smoke. Do you understand the problem? So you cannot change the frequency. You cannot change the frequency. Of course, you can increase the frequency, you cannot decrease the frequency by keeping the voltage constant. So when you change the frequency, what you usually do, you maintain V by F constant. Why? Because V by F will give you 4.44 in phi m. So that means you are using maximum phi m what you have designed your motor for. So V by F is the method for controlling the speed of the induction motor.
Where does that limit come from? Where does the BH limit come from for a particular material? Is it related to the conductivity of the material?
The BH limit comes from the BH characteristic of the material what you have used. So basically this will be the material what you have used for making the motor. So usually we can say it's a silicon steel.
So if you use like a superconductor or something, the BH characteristic.
Superconductor is
That's the
nothing to do
hysteresis in the
with the
core.
material of the motor. Superconductor is the carrying current. That's different part. You have to have material which actually produce your flux. So that's the core material.
Do superconductors produce flux?
Superconductor is carrying current. So that's you're replacing the winding, not the core. Yes, Robert.
So just with hysteresis, is that like a fundamental thing, or do we just like test a whole bunch of materials, see how they react?
Is the fundamental thing. So material characteristics, this is one of the problem for our degree program. We do not cover too much material, but material is very, very useful. So if you do not have this concept clear, you will not actually get it. That, oh, how can I do? I can make the B 10%, 20%. But you cannot do that. You understand? Those who does not know the background of the material, they may say, oh, I can make the B 20% more. But 20% more, you just cannot do that. You can make only 1 or 2% more. 20% more means that you are actually damaging everything. So this is the fundamental thing, the BH characteristics. So material 8. So you talked of superconductor. Superconductor is replacing your winding coil. Okay? Superconductor does not replace your core. Your core is the material which actually provide the flux path of the flux. Okay? You produce the flux by the superconducting coil, but that flux has to go through. So that's the path you get from the core. So silicon steel is the material you use, and this maximum value is around 1.6 Tesla. 1.6 Tesla, which is the maximum flux density you get. So we usually use this method, V by F control. So if you change the frequency, you need to change the voltage too, so that the ratio between the voltage and the frequency remains constant. Now, if you follow the curve, so what happened? You can have something like this, V by F constant, but when the frequency is very less, you cannot decrease the frequency, a voltage too low. This is just to overcome the loss in the stator winding. There will be some voltage drop in the stator winding, so you need to increase the voltage slightly higher. Otherwise, you will not be able to get the sufficient torque.
So there's a minimum running speed.
Yeah, so you have to have minimum. So there are some power which you need to overcome, stator copper loss, rotational losses. So your voltage should be slightly high at low frequency.
So at what sort of speed or S would V on F not be constant anymore? Where would that curve
So
reach?
usually this can be like, let us say you can go for around 10 to 15% of the full load speed. So if you are 50 Hertz, you may say 5 Hertz below, maybe below 10 Hertz. So it comes like 5 to 7.5 Hertz, isn't it? For a 50 Hertz system. So below 10 Hertz, you should not follow that V by F constant.
for a low speed, does that change the hysteresis characteristic shape at all? Or?
This curve?
Yeah.
No, this curve is the material characteristic.
Yeah, I thought so. I just wanted to check.
This is the material characteristic. So you will find that material characteristics which independent of whatever you do. Okay? So this comes from the material characteristics, which is called intrinsic property of the material, BH characteristics. So BH characteristics you are not changing.
Yeah.
You cannot change. Of course, you can damage it. Then motor will behave in an erratic way.
Yeah, because I'm just thinking the VM equals constant obviously breaks down around the 10 to 15% area, and I'm trying to think of how that would affect that V equals 4.4 F and phi thing.
Yeah. So that's why
And
V will be a little bit more.
Yeah, so
So V will be a little bit more. So you actually more voltage.
and that's to avoid having too much flux and thus too much
Yeah.
current.
So now what actually happened if you go back to my earlier circuit. So basically what actually it does. So if you think of that situation what we have. Okay. So this part, your RS and JXS, they actually drop some voltage. Then only you are creating the flux.
Yeah.
So that voltage drop need to be compensated.
Okay, yeah.
So even though you may say, is it increasing more flux? It's actually not increasing more flux because your flux created by this part of the voltage.
Yeah.
So you just to overcome this drop, you have to increase the voltage slightly.
Right, yeah. So
Everybody got it? What actually you are talking about? So what I said that if you decrease the frequency below a certain value, you do not follow the V by F constant. You rather increase the V slightly. This is due to the fact that you have to overcome the drop in the stator impedance. So that drop you need to provide by increasing the voltage slightly, so that you create the flux which is pretty similar, pretty constant value.
So when you're in that nonlinear region, that V 4.44 changes. Because
No,
you're-
it just doesn't change. So you may say this voltage is actually increasing, this flux, but this voltage is not the. So you may say this is actually E, okay, and V minus E equal to I RS plus JXS.
Okay, right.
Okay, so that expression what we wrote, that's the like basically ignoring the voltage drop in the stator impedance.
Yeah.
Okay, so when the voltage is low, you have to increase the voltage so that you overcome the voltage drop in the stator winding. Any questions? Anywhere you have any issue?
In the exercises we have, like in the lab last week, so I calculate the value of V over F. So it's basically drops from 6 to 4.3. Is that normal? Because that has to happen. Because it didn't.
So
obviously
I don't get what exactly you are talking about.
The value of voltage over frequency
Okay,
in the last exercise we had in the lab.
okay,
So its frequency start from 10 hertz and then finish at 55 hertz. And then the value and the speed start from 300 and end up in 1500.
so you set the frequency.
Yes.
You set the frequency, but you cannot.
Or measure the voltage.
You measure the voltage.
Yes.
Which voltage is this voltage?
It was the line voltage.
Yeah. Is the line voltage which you can see from the display of the.
That's right.
Yeah.
Okay, so and you can calculate the V by F. So then what you get?
Started from 6 and then the last one was 4.3.
So okay, so how many values you have around 4.3 or close by?
Where was the way?
10. So the increment of 5 hertz.
So where it starts 4.3?
Yeah,
The last one 4.3.
Last 4.
The last two frequencies that we tested were
So 50 and 55 go 4.3, yes, and everything leading up to that is also statistics.
no. It increases after here. VMF.
Was it increasing linearly or was it decreasing?
No, but this looks pretty good.
Because it might be that
It's the last 2 points there.
Yeah, last 2 points I don't know. Maybe because you are going beyond 50, 45, 50.
Well, the motor was
No,
rated.
this is not the speed. This is not the.
Yeah, well, the motor was rated to 50 hertz, right?
Yeah, here, you're right. This is sorry, you're right.
Okay, so what you've got here, definitely this one is out of the way because you are not supposed to give more than the rated voltage. Okay, so when you go beyond 50, the motor clamps the voltage to the rated voltage. Okay, so that voltage will be ratio will be definitely less because voltage is less. But 50, you got 4.76, and you go to 25. So 25, you got 5.08. So looks like this is based on, because there are some settings. There are some settings. This is based on sleep compensation or sleep uncompensated.
slip compensated.
Okay. So of course I don't know why it will be like this.